Similar triangles. Here we go. We're continuing on down, getting more and more specific, looking at more and more things. Kind of dark. Am I kind of dark? I don't know. Lighting in this current temporary setup isn't very good, but it's fine. It's fine. No problem. It's no big deal. Let's jump in. So there are different ways to prove that triangles are congruent. There are different ways to prove that they are similar. The first one is angle similarity. So what does that mean, right? So again, we're talking about specifically triangles. If we know two angles, so if we know that this angle and this angle are congruent, then we can say that the triangles are similar. So the point here is that for similarity, all we have one way, there are three ways to prove that triangles are similar. If we know two angles are similar, we know the whole triangle. We don't need all three angles. We don't need angle. That's not even a proof of congruence, right? But angle all by itself, we don't have to have all three, just two of them, and we can prove that the triangles are similar, right? So that's nice. Easy peasy. Let's take a look at a couple of examples and go from there. So we've got a couple of different problems here with the same directions. We're going to determine whether the triangles are similar. If so, write a similarity statement and explain your reasoning. So the similarity statement is like basically the proportions, right? The proportions equal to each other, and then explain your reasoning. We're talking about what theorems let us get there. So let's start with this number one problem right here. So we have angle, right, of the angle, but we don't have angle yet. We just have a single angle. This guy is congruent to that guy, right? So that's a good piece. So can we get to the other bits? Well, let's take a look. So this guy right here and this guy right here, we can find using the triangle angle sum theorem, right? The triangle angle sum theorem. So if this works out, that's our explain our reasoning, right? The triangle angle sum theorem, right? If this works out. So that tells us that all of these angles add up to 180. So 57 plus 48 equals, pop that in here. So 57 plus 48 equals 105. So this is 105 plus the measure of angle K equals 180. Right, and then we subtract 105 from both sides, and we get that the measure of angle K equals 75, right? So now we do, in fact, have angle. So yes, similar. Oops. Because of this, for one thing, and angle similarity, right? That's the only one we know so far. So if it's a proof of similarity, it's going to be that one on these two problems, right? So this guy. So do we have angle? Let's see if we can walk through what's going on. So we have these two angles that are congruent, right? This angle, oops, clicking the wrong buttons on accident. Go back over here. You go away. What are you doing? What's happening? Everything's going crazy. Computer's going weird right now, but see if we get through this video and then I can restart or something. I don't know. Something's weird. Anyway, what we were saying was angle RSX is congruent to angle WST because of the vertical angles theorem. Right now, we also have what do these excuse me, what do these little arrows mean? That means that XR and WT are parallel. So we got all our parallel things. We've got this right here. These two are alternate interior, and that means they're congruent. So yes, similar, or we can, instead of yes, similar, we'll do this one a little bit more formal, a little more correctly. So triangle XRS is similar to triangle TWS because of vertical angles theorem. Angles theorem. And alternate interior angles theorem. Angles theorem. And then finally, because of angle, right? And angle. So you can see, we didn't really do this as a full formal proof, but you can see that in that this, like if it said prove this statement, we could go through and do those lines of proof, right? We could say that angle X is congruent to angle T because of alternate interior angles theorem, right? We could say that angle RSX is congruent to angle WST because of vertex angles theorem, right? And then we could finally say that they're similar because of angle. So you can see how that's kind of what we're looking at here is instead of doing this as a full proof, kind of giving ourselves and the question asker the steps that we would take if we were to write this as a proof, right? So that's what we got going on here. So next, there are two other ways to prove that triangles are similar. So what they are side similarity. Now this is different. This is different than side congruence, right? Because in side congruence, it has to say that the sides are congruent, right? But that isn't necessarily true. The sides don't have to be congruent for triangles to be similar. They have to be proportional, right? So if we can prove that all of the sides are proportional, so like if we were to write out the side similarity for these triangles, we would say that the measure of PR to the corresponding one, the measure of LM equals the fraction of the other one. And we would have to have them all. So the measure of RQ over the measure of the one that goes with the other triangle, the measure of MN, right? The measure of MN equals the measure of PL to the measure of LM. That's not right. PR. L is in the totally other triangles, like on another planet or something. How about PR to LM? Right? So we would have to have, in order to use side similarity, we would have to have all three sets of sides are proportional to each other. So we have to have all of this. So side angle side is a little bit easier than side in a way. It still has three things, but for side angle side, you probably could figure this out just based on all the puzzle pieces that you have in your head now, is that you have to prove that two sides are proportional and the angle in between them is congruent. So you could write three different ways of doing it. I'm going to write this as an example because there are actually three that you could write for this set of triangles, because we could do with angle T and A, we could do the sides on the side of U and B. We could do the sides adjacent to V and C, right? So you can do them all. You can do all or them all or any of them is maybe a better way to say it, right? So in order to use this in this example, we would have to say that the measure of TU to the, right? So fraction measure of AB, so the one that is corresponding, AB is proportional to, and it'd have to be this side. Like you couldn't use in this, if we had angles T and A, you couldn't use side UV and side BC. It has to be the ones that are adjacent to the angle for side angle side similarity, right? So it's proportional to TV, measure of TV, to the measure of AC, right? And angle T is congruent to angle A, right? And we could write the same sort of statement for all the rest of the angles, right? It would just shift the sides that we needed to use for the thing. All right, let's hit some more examples. Oh, disaster. Yeah, okay. So, same thing, same instructions, different pictures. Determine whether the triangles are similar. If so, write a similarity statement, explain your reasoning, all the things, right? So, on this guy, we need to look at these. We have three sides. So, if these triangles are in fact similar, now we could I'm getting ahead of myself. We probably want to do side similarity. Now you could arguably, because we got vertical angles. Now you may be saying we also have parallel lines. There's nothing on here that says parallel, right? If it's not written, it's not true, right? We also have vertical angles, so you could also go side angle side. But this one we're going to do side just because we have all the sides and we're going to include an example of that, right? So let's take a look at the things, right? So we've got 6 to 15. So 6 to 15. And we want to know if that equals, and we're going to make a guess that it's 5 to 12 and a half. It could be 5 to 20, and we may do that in a minute if this doesn't work. So 5 to 12 and a half. The point of that, and that point of the point of that little outburst is that you don't necessarily, unless it says somewhere, you don't necessarily automatically know which sides correspond to which, and so you may have to try different tactics. And we want to see if that equals, or different combinations to see if it works. See if that equals 8 to 20. 8 to 20. So let's reduce these fractions on down, right? So what is 6/15 reduced by? It reduces by a 3. So 6 divided by 3 is 2. 15 divided by 3 is 5. So does that equal, this one's a little bit harder to reduce by hand. I'm going to do it on the calculator. Now you could multiply both by 10 and get 50 over 125, and that actually doesn't sound very hard. 50 over, little scratch paper, 50 over 125. You could totally put these in the calculator and see if your decimal matches exactly, or if the reduced fractions work. So, 50 over 125, and then reduce it by 25. So this would be 2 over 5. Right? We could also come over here in the calculator and do 6 divided by 15 equals 0.4, and then 5 divided by 12.5, 0.4. So you can compare these fractions different ways, right? But I already started this kind of more middle school reduce the fractions way of doing it, which is good practice. We got to get that practice in. We can reduce these guys by 4. 8 divided by 4 is 2. 20 divided by 4 is 5. So, therefore, as a smiley face, therefore, triangle, I think I'm going to move this over because I'm going to run into not having enough space. Whoosh. Can't do that on your paper. All right, brush. Triangle PQR is similar to triangle STR because of side, side, side similarity, right? Okay, let's take a look at this guy. So this one we don't have three sides. So this one we couldn't even do it this way if we wanted to, right? So this one here we don't have, because we don't have this side down here, right? So since we don't we don't have that side down there, then we either need to look at angle or we need to look at side side. We're going to have a hard time getting angle because it's going to be hard to get these kind of bottom angles there. But this one, by the reflexive property, we can do this one. Now, this is a note on naming this angle. You'd be tempted to say angle A, and you might argue that, but there's technically kind of two angles there. They're just defined the same way. So I don't know. We can say angle A or we can say angle EAF. It's debatable what would be allowed and whatever else. I personally wouldn't stress too hard. So all we need to do is we need to figure out whether the sides are similar. Now this is a little bit tricky, right? Because we've got this triangle here, this little one here, but the big one has actually got this kind of segment addition thing going on, right? So in order to figure out whether they're similar, we need to find this large length here and this large length here. How can we do that? Well, easy peasy, right? I basically just said how to do it, right? We have segment addition here. So to find these big lengths, we just add them up. So the length of AB would be 15, right? And the length of AC would be 12. Because 10 plus 5 is 15, 8 plus 4 is 12, right? Easy peasy. No big deal, right? So let's check the proportions, see if they work. So 8, that's the side of the little one, to the side of the big one that corresponds. So 8 to 12. Does that equal 10? That's the side of the little one to the side of the big one, so 10 to 15. Now, just for grins and giggles, I kind of sort of showed a couple different ways to check it. There's actually one more way to check this. We could also, just like solving a proportion, cross multiply and so 8 times 15 and 12 times 10. So 8 times 15 would be 80 plus 40, so 120. So 120, does that equal 12 times 10? 120. It does work. So, therefore, triangle CAB, so the big one, right, is similar to triangle EAB, so the little one, EAB, because of side similarity. Easy peasy, right? Oh, and I should put, there's one more thing we use, right? And reflexive property. Reflexive congruence. And I only make that note because of the next thing I'm about to show you. And that is these properties apply to similar figures as well as everything else that they apply to. So reflexive property is applicable when we're talking about similarity. Obviously, reflexive property is like applicable to everything because of course it is. Triangle ABC is similar to itself. Triangle similar to itself. Symmetric property works if triangle A, I'll just read it all out. If triangle ABC is similar to triangle DEF, then you can flip it. Triangle DEF is also similar to triangle ABC. Makes sense. Transitive property, which we've used for congruence and all of these other things. for parallelness. These all work for that as well. Then so it also works. If A is congruent or A is similar to B and B is similar to C, then A is similar to C is really what we're saying. We just worked with triangles, works with similar figures. It's great. The fact that these properties are applicable in so many areas shows, in my humble opinion, the robustness of math. We've got one more thing to see, and then we're going to be done. So we've got this. These kind of problems are the most fun kind of problems in this unit, in my opinion. So we've got these triangles here, and we're supposed to find the measure of BE and the measure of AD. So I'm going to real quickly kind of highlight what we're looking for. What is happening here? Am I hitting the wrong button? I guess I was. So highlighting what we are looking for. We are looking for BE. So that's this one. And we are looking for CE, right? That one right there. So that's that one. All right. No, that's not at all what we're looking for. Why didn't you stop me? How about AD? So this one. So we're looking, those are what we are looking for, right? Easy peasy. So let's take a look at what's going on. We've got this triangle here and this big triangle here. So I'm going to kind of figure out some of the sides that are happening, right? So we've got our little triangle, which includes BE, right? So BE equals X. Should stick with the blue because that's the thing there. So it's got X. That's X. AD. Where's AD? Oh, I still didn't label the stupid thing right. It's okay. It's okay. Don't. I'm okay. I promise. I'm okay. Are you okay? Are we okay? I don't know if anybody's okay. How about AD, which is this one right here? So what does AD actually equal? AD equals, okay, so here's funness. It equals y plus 3. It's got a segment addition here. So this is x, and this is y plus 3. Right? So you're like, oh no, am I going to have to do a system? Maybe not. Let's see. So do we have any corresponding sides all of the whole fraction, right? So one thing I kind of stopped over and then got excited with colors and then we just like went nuts is before we can really solve this problem, we need to know, are the two triangles similar? Well, they are, and we can tell they are because we've got angle here. We've got angle, and then we've got this is by reflexive property, and then we also have corresponding angles on parallel lines. So this guy, switch. This one is congruent to this one. So by angle, these are similar triangles. So we can set up proportions and whatever else. So we do have one side complete with all the numbers we need because we've got 3 and then we've got 5 for this big one. So we know we can go, I'm going to label this as little. That's what I thought. Little to big. Sometimes it's helpful. I think I said this on the last lesson that sometimes it's helpful to kind of put words with where the fractions are, because the only time that you're gonna make a mistake, likely, if your algebra is even vaguely decent, right? The major place you're gonna make a mistake is if you have the wrong sides corresponding. So doing things like this can help us kind of keep track of where we're putting numbers. So the little side 3 to the big side 5. So the scale factor between these two triangles is 3/5, right? This is reduced all the way. So we can set up some other things that go with it. So X would go with CD, right? So X to the measure of CD, that doesn't sound particularly nice. So hopefully we can do something else, because that's like not hardly useful because it's like variable. We've added another variable on here, right? So hopefully we can find something else out before we have to deal with the X one. Let's keep going a little bit, right? So this also equals this side here. So y to, that's the little side here, that's the AE, to y plus 3. Now, looking at these equations here, do we have any sets of fractions that only have one variable? Well, yes, we in fact do. This one has no variables, and this one only has one variable. So those two we can use to go ahead and find y. That might help us out, or that's going to get one thing. That's going to get us started. So let's excuse me. Let's use that to find at least y, which will give us, that will probably give us AD, this pink thing we're looking for, right? So let's go for that. So we've got 3 to 5 equals y to y plus 3, right? So this we can solve by cross multiplying. That's easy peasy, right? 3 times y plus 3. I'm going to write that all the way out because we don't want to make a mistake and forget that we need to distribute. So y times y plus 3. 5 times y is just 5y. That one we can just write down and go. So right here, we need to distribute. So this multiplied over here. So 3 times y is 3y. 3 times 3 is 9. So plus 9 equals 5y. So now let's finish solving for y. So let's subtract the 3y from both sides. Minus 3y. That cancels. So 9 equals 2y. So we can divide the 2 off. So we end up with y equals 4.5 or 4.5. I'm going to write 4.5 because I know you're more comfortable with that. That's fine. Decimals are ugly, but that's fine. You don't have to necessarily agree with me on that. Hey, so we need to find BE, so we can go ahead and plug that into, the wrong one. No, AD. We do need to find BE, but we need to find AD. That's the pink thing, and we've got Y. So we can go ahead and substitute this 4.5 in here. So 4.5 plus 3, which means that the measure of AD equals 7.5 units, right? That's easy peasy. Now, how are we going to get to X? Well, the astute among you may be like, okay, well, you can't get to X. And you'd be right, because I forgot, when I was copying this problem down, I missed something, and this was supposed to be labeled as 3.5, which is good for us, because otherwise we don't have a tool in our tool belt to find that, because there's too many variables. So we kind of erase here and turn this into 3.5. Pretend like that never happened, right? I mean, it's on camera on YouTube, but we'll pretend like it never happened. So now we've got no variable, and we've got one variable. We can use that proportion, and we can solve for X, which is great. So 3 to 5 equals X to 3.5, right? That's easy peasy. 5 times X is 5X. And 3 times 3.5 is 1.5 plus 9, 10.5. Let me verify. 10.5. I don't know. They skipped too far. So verify with this guy. 3 times 3.5 equals 10.5. Yay, I did it. 10.5. So we're going to divide by 5 on both sides. Divide by 5. X equals 10.5 divided by 5 equals 2.1. which we probably could have gotten in our heads, but you know, a little sanity check never hurt anybody. That equals 2.1, which means that the measure of BE, because it equals X, is also 2.1. And that is it. Thanks for joining me today in Similar Triangles. We'll see you next time. Peace out.